Before we begin, let me just do maybe a couple of real quick announcements. I can't remember if I told you this last time or not, but I thought I had completely finished the spring schedule, and yesterday I got one email and one phone call about things they want to change. Some of the faculty members want to change, so I'm going to try to do that, but that won't take, hopefully, knock on wood, very long. I have gotten started catching up on my grading, okay? You can see the big stack here. Still pretty thick, but I got all my previous class, the Math 100 class, caught up with grading. I've got this class about halfway caught up with grading. Don't have too much to do. The next class I only got maybe one or two things to do. The following class after that, I've just gotten a few new. I had it caught up, but more things have come in since then. The one I've got late this afternoon, I've got a little bit of grading to do in it, but it's that Tuesday, Thursday afternoon class that we've had a lab every day, and we've had two tests, and I've just got one lab and one test done. So that's the one that's going to eat up most of my time. However, I'm going to get moving. I am moving on it. I'm going to whittle it down as much as I can, as soon as I can. It might be Friday or the weekend before I get it completely caught up. And then at that point, I've got to get all the grades in Blackboard. So there's still quite a bit to do, but at least I've got the time to do it now. I hope I can. All right, now there's that. Another thing is tomorrow, normally on Thursdays, Tuesdays, and Thursdays, my office hours are 11:15 to 3:15. However, tomorrow we have a faculty meeting. Fortunately, it's on this campus at 2:30. So my office hours will be shortened a little bit to be 11:15 till around 2:15, 2:20 or something like that, because I have to go to the faculty meeting, be there about 2:30. So just a little bit, 45 minutes short or something like that of office hours. Is that right? Yeah, something like that. A little bit more than that, perhaps. Okay, so other than that, so that cuts into some of our grading time, but it's not that significant. Okay. Can't think of anything else. Oh, I think I told you all this last time. The good news, bad news. Okay. Sorry about that, but I won't see you again for a week. Okay, after today. Okay. Because Monday's a holiday. Better say. Okay. So, you said let's go back to that last example?
Yes, sir. We can just
and what?
Just talk through it. You know,
okay.
You like to go through it and
then... Okay. All right. Now, I don't know if the PowerPoint even had that one, did it? Okay. All right. Now, let's find the area of the surface formed by revolving the graph f of x equal x squared on the interval from 0 to root 2. Okay, now that's where x is equal to 0 to root 2. They're not super clear about that, but that's usually how they express it. When you revolve that around the y-axis, okay, and they show this in the picture, okay. Now, what you have, here's how I remember area of revolution. It's the arc length times 2 pi times the radius. Okay. Now, the arc length would then be, remember how we did arc length? You take the derivative of the function, that would be 2x, okay? Then you square that, and that gives you 4x squared. Then you add 1 to that, and that's 1 plus 4x squared. And then you take the square root of that, okay? So that gives you your arc length part of the problem, okay? Now, the 2 pi r, if you look at the figure there, your radius of revolution is just going to be your x, Okay, your r of x is equal to x, because that's how far you are from the y-axis. That's what you're revolving around. So the first part of that would be 2 pi. That can be outside the integral. The integral from 0 to root 2, that's your limits on x. The x, that's the variable x, that's your radius, times your arc length, which is the square root of 1 plus x squared, and then you do the dx. Okay. Now, to do that, we chose to use the substitution method. Okay. And we chose to have the u be what's inside the radical, 1 plus 4x squared. Okay. When you did a du of that, you get 8x dx. Well, you have an x out there in front, you just don't have the 8, so I'd go and divide by 8 on the outside. We already had a 2x out there. When you divide by 8, that gives you 2 pi out there. When you divide by 8, that gives you pi over 4. So that's where that comes from. And then you have your u du. No, square root of u du. Because the u was 1 plus 4x squared, and you do the square root of that, which is, I would say, u to the 1/2 power times du. And you integrate that by being u to the 3/2 power over 3/2, or times 2/3. Okay, so that 2/3 combined with the pi fourths would give you pi 6. 2/3 times pi fourths is pi 6. Okay, and then if you substitute in, we didn't change our variable change the limits when we changed the variable to u. When you did change the variable to u, I'm going by memory here, it went from 1 to 10, was it? 9, 1 to 9, okay. And then when you do your...
so that's the part that I was confused on when I was looking back, is where the... So we got 2/3 times u to the 3 over 2.
Okay.
This is the part
All right. Let me find okay, here's some white space. All right. See if I can reproduce what I just said. Okay, I think we got to the point of being, let me get my pen reactivated. Okay. I think we're at the point were you okay at the pi fourth point, or
no,
you were?
What's going on when it's s equals pi over 4 integrated from 0 to 9, and then we have u to the 1/2 du.
Okay, what was the out front, in front of that? 2 pi or pi fourths or what? Pi fourths. Okay, pi fourths, the integral from, what is it, 1 to 9?
0 to 9.
Was it 0 to 9? 1 to 9. Because when you plug in what your u was equal to 1 plus 4x squared, right?
Oh, yeah, that's right. That would be.
When you plug a 0 in for x, that gave you 1. And when you plug a root 2 in for x, that gave you 9. Okay, got it. Okay. Now, that then had you u to the 1/2 du. Because we had already pulled out divided by the 8. Yeah. Okay. So, that integration gives you pi fourths, u to the 3/2, and then you either divide by 3/2 or multiply by 2/3, right?
I guess I'm just confused on where the, like, why does it go from u to the 1/2 to u to the 3/2?
Okay. Oh, when you integrate, you add 1.
Oh, yeah, that's right. That's right.
Yeah.
Yes, I got you.
Okay. Okay. It's anti-derivative, right?
Right.
Derivative, you subtract 1, Antiderivative, you had one. Okay.
Well, that's a loss for that.
Okay. So you all right with that part then?
Yes, sir. Good.
And from there on, or you want to go on with it?
That all makes sense from there on out. I'm just kidding.
Oh, then let me get back up then. We can't have it making sense. Okay. Okay, and that's where the 2/3 came from too. It's reciprocal at
Right.
3/2. And so that'll be,
Well, I couldn't think of that.
all right. So that's okay.
Yes, sir.
All right, good. That was easy. Or it did require lots of strain. All right, then if we're going to start working finally, okay, 7.5 is dealing with work. And only two objectives here: find the work done by a constant force and find the work done by a variable force. Sounds simple enough, doesn't it? So the work done by a constant force. In general, work is done by force. This gets into a little bit of physics here. When it moves an object, okay? Am I doing work on the desk here?
Yes.
Yeah, you would think so. I might be sweating and cursing and everything else, but if that desk isn't moving, by physics, I'm not doing any work. I'm just pushing on it, not doing work, okay? And usually in my physics or physical science classes, I give the example of when I was digging out the patio behind our house, I hit a boulder. It was a huge rock. I mean, it had to have been at least that tall and that big around, and it was solid. And I dug and pried and twisted and did all sorts of stuff. I did no work on that rock until I got it to move. Even though I was sweating, taking lots of time, burning lots of calories, I was doing no work on the rock until it moved. So when it moves an object, a force when it moves an object, if the force applied to the object is constant, then the definition of work is pretty simple. If an object is moved a distance d in the direction of the applied force, constant force F, then the work done W, capital W by the way, by the force, is defined as work is equal to force times displacement. Okay. I like the term displacement rather than direction. Direction to me has no movement with it, just a direction, so displacement I like better than direction. Okay. Oh, distance. No, it's distance. And force times the distance, that's fine too. Okay. Now, since you've had some vectors at this point, you have had dot products of vectors, or not? Cross products, dot products, not, or you just had vectors. Okay. I keep forgetting where that shows up in the book. Okay. Well, later when you get there, the dot product of two vectors is going to produce a scalar. Force is a vector, it has a direction. Displacement is a vector, it has a direction. That's why I like displacement. But when you do a dot product, that gives you a scalar quantity. That's going to be work. Work does not have direction associated with it. Now, they did say move the distance in the direction of the constant force. Okay? If I'm pushing on the chair here, like this, my force is like this, but the chair is moving like that. So that's not the product of my force times the displacement. It's the component of the force in that direction of displacement. That's the only part that's doing work. And there again, the dot product comes in to explain that as well. If I'm pushing like that, that is force times displacement. Okay? Because the force is in the same direction as the displacement. So the product of those two would be the work done on the chair. Okay. Now, goodness gracious. This is really physics here. 4 fundamental types of forces. Gravitational force, we're all experiencing right now, right? Okay, good. Electromagnetic forces, you may not feel like you're experiencing, except you're looking at electromagnetic force, light. So there are electromagnetic forces. Then there's the strong nuclear and the weak nuclear. Usually I reverse that and say weak nuclear, then strong nuclear. We're not going to get into what those are. Those are the things that... The strong nuclear, I think, is the one that actually holds the nucleus together. Okay, because if you think about it, what's in the nucleus of an atom? Protons and neutrons. The electrons are out here scattered around, flying around like crazy. Now, the protons are positive charged, the neutrons are neutral, and the electrons are negatively charged. So here you have this nucleus, which is incredibly tiny, but incredibly massive, okay, for that size. So these protons and a few neutrons are packed in there so tight to each other, and the electrons are here flying around, okay? Now, protons are all positive charges, and positive charges repel each other with a very strong repulsive force. What holds them together? Strong nuclear forces. Something has to, because you see, electromagnetic forces actually are stronger than gravitational forces. Difference is gravitational forces act over longer distances than electromagnetic. But if I had a rubber comb and had enough hair to comb and comb my hair with it, I could pick up little pieces of paper. Have you seen that done before? Yeah, little pieces of paper. That's overcoming the gravitational force on that paper. Electromagnetic force is stronger than the gravitational force. That's why they fire up and hit the comb. Okay? Well, in order to overcome those really strong electromagnetic forces that are trying to push those protons apart, you have to have a strong nuclear force holding those together, because they are in very close proximity. But that strong nuclear force doesn't have the range that electromagnetic, just like electromagnetic doesn't have the range of gravitation. It's stronger, but it doesn't have the range. The weak nuclear force is sort of in between those, and it's another force that kind of keeps nuclei doing what they do without blowing up or something. So, a force can be thought of as, and this is physics, physical science again, a push or a pull. A force changes the state of rest or the state of motion of a body, okay? If the golf ball is at rest there on the tee, and I swing that club like crazy and hit it, I change, if I hit it, that's the big if there, then I change its motion from being at rest to taking off somewhere, usually into a bunker or something. But anyway, that's beside the point. Okay, never straight where I want it to go. Or if someone throws a football to me and I happen maybe to catch it, I've changed the motion of the football. I've exerted a force on it to change its state of motion. Okay. For the gravitational forces on Earth, it's common to use units of measure corresponding to the weight of an object. That weight is a force, by the way, either measured in newtons in the SI system or pounds in the U.S. customary system. Okay. Lots of physics here. Why? I don't know. Okay. Here's example 1. Determine the force done in lifting a 50-pound object. What's 50 pound a measure of?
Weight.
That's weight, which is not mass. Mass is how much of the object there is. Weight is the effect of the gravitational pull on that mass. Okay, so this is weight. Now, weight is little w. Work is capital W. So just to keep those straight. But weight is a force. Now, sometimes it's called F sub G, force due to gravity. Sometimes it's called F sub W for S, force due to weight. Whatever you want to call it, it is a force. Okay? Okay, I don't care which one you use. I'll just put the G down because I had it there first. So that's your force. And then obviously you moved it 4 feet. That's your displacement. I like little d, but they use capital D. So what is the work done? Pretty straightforward. Now this is capital W. That's what we're looking for. That is the force due to gravity times the displacement. Because you're lifting that 50-pound object. Okay? Is what? Yes, that would be 200. And the units there would be foot-pounds. Pretty creative, huh? Pounds times feet is foot-pounds. Okay. Now, here's where I usually introduce you perhaps sometime during your lifetime have used a wrench that was calibrated in foot-pounds.
Every day, torque wrench.
Yes, that's not work. That's torque. Torque is the cross product of force times displacement, because that's a different displacement. See, when I push on the chair, the push is in the same direction of the displacement. When you're using a torque wrench, you're exerting a force on this nut you're trying to loosen or whatever you're trying to do here, tighten or whatever, but your displacement is, your force is here, and it's perpendicular to the displacement, right? The displacement is from the socket to the end of the wrench where you're pushing, and your push is in this direction, perpendicular to that. Right. That's a cross product, and torque is a vector quantity. It's a twisting force. So, but it's also measured in foot-pounds, okay? So there's two different quantities use the same units. Work for inline motion and torque for perpendicular twisting motion.
And so that's like for 500 foot-pounds, you could have a lever 500 feet long, and it would take
1 pound.
1 pound to...
Yeah. Or 500 pounds on a thing 1 foot long, I guess, which allows you to use if you can hold it, the 500 foot level.
I also have another question too about this. It's sort of unrelated to...
What's that?
I sort of have another question too. It's kind of unrelated, but
yeah,
to what we're doing anyway. But I thought that they said that gravity doesn't really, like we call it gravity, but it's really more of it's our little, like our planet's like blip in the Jello mold of the universe that is like it's not really pulling. There's nothing really pulls. I don't think, does it? It's
okay, that's it's not string theory, but it's one of the theories that preceded string theories. It's how they kind of model what they think is going on, and the sort of the Jello or the movable fabric of space, and it makes
our planet is pushing in a smooth,
right,
sheet. Our planet is pushing out, and that's what Einstein said.
Okay, sort of. Yeah, he what was that? I can't remember if it's special or general theory of relativity. I think it's general theory of relativity. He addresses the issue of gravity, and his explanation has been shown to be better than Newton's was. Newton just basically used what he could, empirical evidence, and measured it, and seemed to do a pretty good job on the macro scale. But of course, he couldn't do much on planetary or astronomical scale, and Newton, and then neither on the massive or on the micro scale. Of course, he didn't have the tools for quantum mechanics or anything else. So Einstein was able to think through and hypothesize some of these things, and certain things that have happened, people have been smart enough to figure out they could use this to test this hypothesis. And sure enough, so far everything is checked out positively. It was something like a solar eclipse.
Where like a star was in one spot, and then it passed over the eclipse, and they could see that it was bending.
It seemed like it bent the fabric of space, basically. And they said, he was sort of right there, but it's hard to imagine the fabric of space when there's space is by definition nothing there, so you're dealing with force fields, basically, and it's the disturbance in the force field. Well, that then creates a force. So you can't really say it's not a force, because that fabric is sort of a field itself. So it's way deeper than I'm able to address. So yeah, but it is pretty interesting. All right, so yeah, that was example 1. It's pretty simple, 50 times 4. Okay, and as I've already suggested, well, let's just watch how they do it too. We erase this, and look at that. Oh, and I meant to say this, because I sort of glossed over it. Determine the work done in lifting a 50-pound object 4 feet. That's lifting it, that's going upward. Gravity is pulling downward, so you are working against gravity. Now, if you lifted those 4 feet by, now we're going to imagine this, it's probably never exactly true. What if you had a perfectly slick, as an icy slick, inclined plane? And what you're really doing, now you're not stepping on the ice, but for the box or the whatever it is that you're lifting, the plane, there's absolutely no friction there. And you're pushing that up, and let's say the plane is 10 feet long, pushing it up, but lifting it 4 feet. Is that easier or harder than lifting it 4 feet?
Easier.
Much easier. Well, you're doing the same amount of work, but it's not 10 feet. You're still doing 4 feet, but you're taking 10 feet to do it. That is called a force multiplier, and that gets into levers, just like we were talking about that. Like, can you pick up a car? With a lever, you could. A jack? All of you use jacks. Did that pick up the car? And what was the only force on it? Your force. If you're doing a lot of distance, you're moving the lever, and the car is coming up a very small distance, but you are lifting the car. Well, same type of thing here. The force, though, has to be in the same direction. The force that you're pushing here, it has a component upward, but the other component is doing the work, but it is reducing the amount of effort you have to do, in a sense. Because you see, a lot, that plane is supporting this. You're not having to support it as you're lifting it. It's supporting it, and you're just contributing a little bit. So it's a lot of different things there, but the force has to be in the same direction of the motion. Okay, motion here it was this way. Yeah, all sorts of nuances there. But as long as they're in the same direction, all you do is multiply them together. 200 foot-pounds. Okay, the U.S. measurement system work is typically expressed in foot-pounds. You could use inch-pounds. Most people don't. Or foot-tons. Really a heavy thing. But those are sort of bizarre units. In the international system, that's called System International. It's French, so they usually put the noun first and the adjective later, rather than the way we do it, adjective noun. That would be noun adjective, System International. The basic unit of the force is the good old Newton, named after Sir Isaac, who came up with a lot of this stuff. And the force required to produce the acceleration of 1 meter per second, 1 meter per second squared, on a mass of 1 kilogram. Okay, that's where mass and forces come together. You have to have that acceleration. Okay, so mass is not a force. A force is a mass times an acceleration. This system work is typically expressed in Newton meters, but a Newton meter also has the name of joule, and that's sometimes mispronounced badly, but it's named after James Prescott Joule, who did a lot of the early work with quark, okay, and joule equivalent of work, that kind of thing. So a Newton is a capitalized, the term itself is not, but when you use the abbreviation, like foot-pounds are not named after anybody, they're feet and pounds, But a Newton named after Newton is capital N, because it's named after Newton. A joule is a capital J, because it's named after James Prescott Joule. Okay. And another system is called the CGS system, and most of the time I did not used to capitalize those. Then the basic unit is the dyne, is a force, and a dyne times a centimeter would be an erg, but they don't even mention that, do they? Wow.
It's in
Okay.
the book.
Huh?
It's in the book.
Oh, it is in the book. Okay. I want.
Oh, it's right.
Yeah, there it is. Erg. Okay. But it wasn't mentioned in the paragraph. Oh, there it is. Second paragraph. That system work is typically expressed in dyne centimeters or ergs. Or Newton meters, that would be joules. Okay. Now, I can hardly resist this. My brother came home from college and told this one. If this is a centimeter, what would this be? An erg is a dyne centimeter. Dumb joke. Okay.
It's a good way to remember it.
Huh?
It's a good way to
A
remember
good way to remember. Exactly. That's how I remembered an erg. I don't ever use ergs, but I knew it was a dyne centimeter. Dyne. Okay, never mind. Okay. Oh, and here's a table. Table summarizes the units that are commonly used to express. They are doing so much physics here, I don't know why. Most calculus books don't even met with the unit. There's several conversion factors. In the U.S. customary system, the measure of work is foot-pounds, measure of force is pounds, and measure of distance is work. That's as foot. That's the standard. And SI system, I wouldn't call it international, I call it SI because that's the standard abbreviation for it. The measure of work is a joule, measure of force, what that vertical line is there, bugs me, is a Newton, and then the measure of distance is a meter. So that would be, Newton meter would be a joule. The CGS system, which I usually, we never use to capitalize because centimeter isn't capitalized, gram isn't capitalized, and neither is second. So they put it capital. It's the measure of work would be an erg, and dyne is the measure of force. And notice you don't just say D, you have to do D-Y-N. Well, why not put the E on it and spell it, and then centimeter is the distance. The conversions are 1 foot-pound is equivalent to 1.35 blah, blah, blah joules, or 1.35 times 10 to the 7th ergs. So that gives you the, okay, and the Newton is 10 to the 5th dynes, but a Newton is also only a little over a fifth of a pound. Okay, and a joule is 10 to the 7th ergs, okay, which would be about 0.7 foot-pounds, and a pound is about 4.44 newtons. Okay. I'm surprised that they put all these conversions down. Maybe you'll be using them in problems, I don't know, but here's just a general rule of thumb. A foot-pound and a joule are awfully close. I mean, that's only a factor, that's, 36% difference. That's just pretty close. A Newton and a pound, that's a lot more difference there, by 80% difference, 80% difference, something like that. Okay? Pound and newtons, again, about 4 times more. So a pound is heavier than a newton. 4 times heavier, almost 4.5 times heavier than a newton. But a foot-pound and a joule are awfully close. Well, why is that? Because a meter is like 3 times, more than 3 times the length of a foot. So the meter is bigger, the newton's smaller, so the joule is just a little bit smaller than a foot-pound. Not that it matters any, but just give you a ballpark. And again, here this indicates joules and foot-pounds are close together. All right. Any questions?
We'll go to McDonald's and order me
What's that?
a Newton cheeseburger. How much a quarter pound?
Yes, you got it. Here's another way to remember Earth. Work and energy or have the same units. Okay, energy is the ability to do work, and work is the transfer of energy, basically. So they have the same units. So ergs also measure energy, and if you think about it, if you put NE G watt, erg is basically a short form of energy almost. Take out the N and the E. Oh wait, just the middle three letters. EN, ERG, Y. So it's the middle three letters almost in energy. I'm not sure that's where they came from. I wouldn't be surprised if it isn't, but that's the other way I remember. That's a unit measure for energy because, or work, because it almost has, it's the middle part of energy, the word energy. Okay. Just little things I use to remember stuff. Okay. So, work done by a variable force, this is over on page 486. When a variable force is applied to an object, calculus is needed to determine the work done because the amount of force changes as the object changes position. Okay? For instance, the force required to compress a spring. Let's think about that. Okay. If I had a spring lying here on the table, horizontal spring, this end was fixed in place, and you would pull on the spring. If you pulled a little bit, the spring pulling back on you a little bit, right? If you try to pull it further, it pulls harder back, right? Okay? Or if it was an open spring sort of, if you push against it a little bit, it pushes a little bit back. But if you push harder against it, it pushes harder back, right? That's what springs do. So they vary the force according to your displacement. That's called the variable force. So if you're doing work with a variable force, you do some work when you do it this much, more work when you do it the next bit. Yeah. So it's varying as you go. That's where calculus comes in, because now you have increments of work, of force that you're using. Okay? Now, consider an object. I've got some gnat that's trying to get into my eye. It did. And I still see it flying around a little bit. Consider an object that is moved along a straight line from x equal A to x equal B by a continuously varying force that's some function of that displacement, x. Let delta be a partition that divides the interval from A to B into subintervals, where the first subinterval would be x of 0, the next one x of 1, x of 2, x of 3, up to x of n, which would be at B. Okay? And let delta x sub I be the difference between any of those little increments, x of I minus x of I minus 1. Okay? For each I, choose some ci, some value in between x of I and x of I minus 1, such that, x of I is less than or minus 1 is less than or equal to c sub I, which is less than or equal to c minus 1. Less than or equal to x1. I'm an xi. That bothers me. Okay, then at C1, that point in between x of 1, I minus 1, and x of I, ci, the force is F at Ci, and it varies all along there. That's the force at that particular point, because F is continuous. Okay? Note here, continuously varying force. So the F of x is not strong and then jumps up to some other level. It's not a discontinuous force, it's a continuous force. Okay? Because F is continuous, you can approximate the work done by moving the object through a subinterval by the increment delta W. Now that's the change of work in that subinterval I. And that would be approximated by the force at that Ci in that interval times the length of the interval. Because if it's small enough, then that's almost a constant force in that little interval, and that would be the force times the displacement. That's what that is. Okay? As shown in figure 747, which is a pretty big plane, the total work done as the object moves from x equals A to x equals B And I do not know, oh, I guess I do know. Oh yeah, here we go. What I think they tried to do was highlight that box, and they wound up making it so you can't read the box, okay? What that read, it's in your text, is W is equal to, and that's capital W, by the way, is equal to the sum from I equal 1 to N of your incremental work, W sub I, okay? And the incremental work is that force, this is your incremental work right here. So that goes full circle. If the work is a summation of all the increments of work for all those little intervals that you have there, the total work would be that, then that total work would also be what that increment is F sub I, F sub Ci, F of Ci times delta X sub I. Sum all those up, which would be force in this one, force in that one, plus the force in that one. So you're summing all those up after displacement of that. So think of it this way. And constantly varying force this way, as long as your delta X is small enough, it's almost a constant. Okay? So that would be your F of C sub I, if I is some point on this interval here, C sub I is some point on there, then you're going to use that to be the average value for all those. And then that force comes out of this question and gives you that little increment of work. Sorry that they messed that up. Okay, this approximation appears to become better and better as your del, your partitioning gets smaller and smaller and smaller. In other words, your number of partitions is going to infinity, making each increment that much smaller. So the work done is the limit as the delta approaches zero. What this thing means here, it means the largest interval in that partition, and that's called the norm of the partition. As that norm approaches zero, then the summation of L from I to N would be that. That then the limit of that approaches zero of the interval. And here's that. Okay. All right. All that to get to the interval. Now, let's think about what this says. This integral, or the summation of all your incremental work as x varies from A to B. So this is varying times your interval. Force times displacement. Same formula, but now it's an integral where this is a varying force over displacement. And that's where calculus comes in and gets it done for you. So much nicer than all those summations too. Okay.
So you can always use integration when you have a summation.
Just about, yeah. Yeah, there's just always a way to express that. Okay. Yes. Oh, sure. He didn't ask my permission to come in late. Why would he ask my permission to leave? I don't know. All right, never mind. Okay, so that is your definition of work done by variable force. And here they say it again, okay? Definition of work done by variable force is exactly what we had. The object is moved along a straight line by a continuously varying force, F of x. Then the work done by that force as the object is moved from x equal A to x equal B would be that the limit as your partition goes to zero of the summation of your incremental pieces of work, and that becomes your integral from A to B of F of x dx. This is your force at any point x times the incremental unit dx that contains that x. That's just what it turns out being. It's a pretty straightforward thing. Now, what I can't figure out, let's see if she's mentioned here. Not yet.
This is in the same page.
What's that?
When they skipped over, this is mentioned on the same page, possibly next slide.
Yeah. The major work by Tweil was a translation of Newton's Principia, is what they usually call it, into French. Her translation and commentary greatly contributed to the acceptance of Newtonian science in Europe. Of course, the people from Britain bought it hook, line, and sinker. They didn't have any problem with accepting Newton's work, but she translated it so that the European, and commented on it, so that the Europeans were able to accept it better because it was in their tongue than French. Okay. French and English never got along, by the way, if you haven't noticed. So she's basically just a translator. That's why I'd never heard of her before I read that blurb. Okay. The remaining examples in this section use some well-known physical laws. The discoveries of many of these laws occurred during the same period in which calculus was being developed. In fact, during the 17th and 18th centuries, or a mathematician, there was little difference between physicists and mathematicians. One such physicist and mathematician was Emily de Breteuil, is how I think you say that, was instrumental in synthesizing the work of many scientists, including Newton, Leibniz, Huygens, Kepler, and Descartes. Her physics text, Institutions, widely used for many, many years. Never had heard of her before that blurb. Shows how the women in science sort of get faded into the woodwork. Okay. So, the following three laws of physics were developed first by Robert Hooke, and you'll notice he was 7 years older than Newton, but he died 24 years before Newton did. And from my understanding, the two did not get along all that well. Okay? They were both from Britain and stuff, and they didn't get along that well. Charles Coulomb, who actually was born 9 years after Newton died, his is the electrical force law. So here's Hooke's law. The force required to compress or stretch a spring within its elastic limits. Okay? What does that mean?
As far as it can go before it starts, like, messing up.
Yeah. Okay. Notice I'm going to lean back on the chair. Does this back go back some? Okay. Does it come back up when I get off of it? Okay. That's called elasticity. It returns to its original shape. Hope I'm not going to do this for you, but if I really wham back on it really, really hard, I may actually exceed the elastic limit of that metal and actually either fracture it or bend it so it doesn't come back to the shape. If it's bent, that's called plasticity because it didn't come back to its original shape. If it actually breaks, that's called the fracture limit. Okay, so you can do either of those things. So as long as you're within the elastic limits, that you haven't sprung the spring, so to speak, that you always come back, then the force required to compress or stretch the spring within its elastic limits is proportional to the distance d that the spring is compressed or stretched from the original length. So F is equal to kd. Okay, now, I have a little bit of a problem with that, in that the force is always opposite to displacement. If I press on the spring this way, it's pushing back. Well, I get it. The force you're exerting on the spring is in the direction of displacement, so it's okay. Where the constant proportionality, K, is called the spring constant. It depends on the specific nature of the spring. Have any of you ever played with a slinky? Okay. That is a spring with a very low spring constant. I mean, incredibly small. But the coil springs under your car are a spring, but an incredibly large spring constant. Try like you might, you'll never stretch or compress those unless you bang on them. Like, okay, I just did a spring here. Yeah, I compressed it. I'd forgotten about that. There's another example. Okay, now, Newton's law of universal gravitation, this was what you said Einstein was refuting or amplifying or building on. Newton's law of universal gravitation, the force F of attraction between two particles of mass M1 and M2, proportional to the product of their masses, inversely proportional to the square of the distance d between them. Now his constant proportionality is this capital G. It was later given a name, sometime or another given a name. It's called this gravitational constant. Also sometimes called the universal gravitational constant. So the force is proportional to product of the masses, directly proportional to that, inversely proportional to the square of the distance. That constant proportionality is G. And that's a universal gravitational constant. If you were to go to some other solar system in the universe, that G would still be good. If you were to go to the moon, that G would still be good. Even though the acceleration due to gravity on the moon is 1/6 that what it is on Earth, the universal gravitational constant would be it's universal. Okay, it's all it is. And it has a value of they left something off here. Oh, no, they didn't. I see what they did. Strange expression of that. Cubic meter per kilogram second squared. What? Okay, here's where that comes from. A force is measured in newtons, and a newton is a kilogram meter per second squared. That's what a newton is. Mass times acceleration. Mass is kilograms, acceleration is meters per second squared. Okay? Now, that's what your force is. The mass over here is a kilogram, right? The next mass is also a kilogram. And the displacement squared is a meter squared. Okay? So, your unit in the middle here has to come out being a newton, which is a kilogram meter per second squared. So, you're going to have to divide this by a kilogram, right? So you can get rid of that. You got to have a meter cubed up here, so you wind up with a meter there, and you have to have a second squared down here. Okay? So what do we get? We got a cubic meter per kilogram second squared. I got the kilogram in the denominator. I think it's cubic meter per kilogram. I think that G is cubic meter. Yeah, okay. Is per kilogram second squared. Yeah, that's the unit. Yeah. Per kilogram second squared, which is a weird sounding thing. What is a kilogram second squared anyway? I don't know. It's just what you have to make the units work. Okay? And that's the force due to gravity. The third one of these is Coulomb's law, which is force between two charges. And notice the similarities. Force between two charges is directly proportional to the product of the charges, inversely proportional to the distance between them. Okay? And it has a proportionality constant, that one happens to be called Coulomb's constant. Okay? And they don't give you that one. I don't know why. They could have. That would be, it would have to be a Newton, because that's what's over here, a Newton meter squared per Coulomb squared. Okay? Coulomb is a unit of charge. Can't think of much more to say about those. Those are just 3 examples of variable forces. All right, here's example 2. Now, you can also, you can also go to larsoncalculus.com for an interactive version of this type of an example. So here's what we got. A force of 30 newtons compresses a spring 0.3 meters from its natural length of 1.5 meters. Find the work done in compressing the spring an additional 0.3 meters. Okay. Now, the first part of that problem almost has to be given so you can come up with the constant proportionality, because we know that force I'm going to call it elastic force, okay, is equal to All right, we know that Hooke's law, I have trouble thinking, is force equal kx, okay? That was Hooke's law, where that is the elastic force of the spring, okay? And we know that 30 newtons here is required to compress the spring 0.3 meters, okay? Now, Hooke's constant then, spring constant, whatever you want to call it, would then be K is equal to 30 newtons divided by 0.3 meters. Okay? And if you take a well, you need a calculator. Just move a decimal one place to the left, the numerator and the denominator, and that would be K would be 100, and the units are Newton per I guess we got it as meters, so Newton per meter, which is sort of standard, okay, which would be 1 Newton per centimeter. I was just trying to figure out which one they would want to call it. They just use that to be.
Where did the 1.3 there come from?
What's the what?
1.3 in the bottom. Oh, that's 0.
It's a 0. Yeah, sorry. Yeah, I slash my zeros. Makes them messy, but it's just an old habit from taking logs in the Navy. Okay. So basically, that first part just gives you Hooke's spring constant, okay, which is K, which is 100 Newton per meter, okay? So that then implies that for any, on that spring, any force, elastic type force, is equal to 100x. Okay, that is with the spring constant in there. So it says find the work done by compressing the spring an additional 0.3 meters. Okay. work done is an integral, and it really doesn't matter where you initiate. So you could say this from 0 to 0.3, or from 0.3 to 0.6, or however you want to do that. Well, I think that'll work for you. Okay, the 100 can pull outside, and you're left with x dx on the inside. Okay, since the formula for this is the integral of alpha of x dx. Your alpha of x is 100 x, so that would be that. Oh goodness, I'm stiff. Okay, not a hard integral to do. What would that antiderivative be?
What?
Second?
Oh, that would be x squared
X
over 2.
over 2, evaluated from 0 to 0.3. All right. I can't read my writing. This is 0 to 0.3. Okay. That'd be 100. Well, let's just do the 100 divided by 2 would be 50. And 0.3 squared would be 0.09. Okay. And that would be alright. I got rid of the 2. So 50 times 0.09 would be 0.45. I believe that's right. And that would be joules. Okay. Newton meters. Newtons is, no. Units are a little funny here. This is Newton per meter. This is meter squared, so that becomes Newton meter. Okay. Nope, sorry. I said it, and then I didn't write it. It's going from 0.3, which was from the original, an additional 3, so you have to do this from 0.3 to 0.6. Okay, sorry about that. So let me back off and get that corrected. The antiderivative is still the same, of course. It's our limits changed here. And this was 50. Okay. You do that. And this will be 0.36 minus 0.9. And all right, 50 times 0.27. My brain's not working well. I think that's right. And that would be, oh man, 35. Okay. 1.35. 13.5. Okay, yeah. 13.5. Yeah. Joules. Yeah. They went about it slightly differently, but got the same thing. Okay, because when I first read this, I interpreted it right, but then when I went to do the integral, I put the wrong thing in. The additional 3 meters meant you started at 0.3 and went to 0.6, so that's why your limits had to change like that. And let's see how they did it, which are very close to the same way. Let me erase this. How are we doing on time? I forgot to bring my watch up.
35 minutes.
Huh?
35 minutes.
To go. Okay, good. I hope that wasn't 35 after. Okay. All right. So by Hooke's law, the force alpha of x required to compress the spring x units from its natural length is alpha of x equal kx. And because we knew initially that 0.3 produced a 30-pound force, it follows that Hooke's law constant would be 100, and that has units of Newton per meter. Okay? Where they spent all that time on units and now they don't use them, but that's okay. So if that's Hooke's constant, then you plug that back in and have alpha x equal to 100x. To find the increment of work, assume that the force required to compress a spring over a small increment delta x is nearly constant. The force required to do that is, you treat it as if it's a constant. Okay, so the increment of work delta W, where delta means change in work, increment of work, is force times distance increment, and the force is 100x dx, delta x, and then getting that into an integral that would be from 0.3 to 0.6, so that work would be 0.3 to 0.6 100x. Bring the 100 out front. Antiderivative of x is x squared over 2. Use the over 2 to make the 100 to 50, and then evaluate there. And they multiplied the 50 by the 0.36 and subtracted the 50 times the 0.3, which is 0.9. So same way of doing, same result, but by multiplying the constant by sooner or rather than later or whatever. Okay. All right. Note that you do not integrate from 0 to 0.6. Well, I did 0 to 0.3 because you're asked to determine the work done by compressing the spring the additional 0.3 meter, not including the first 0.3 meters. Okay. All right. So sorry, my throat is getting so dry I can hardly talk. I'm trying to find where this is. I do not see this. Oh, there it is. They're skipping example 3 is what they're doing. So let's go back and we'll do example 3. Let's see. Okay, let's do example 3 here. Goodness, I'm almost feeling dizzy. Okay.
You need it, right?
Huh?
You need it, right?
I feel like I I can't even talk, could sure use one, but I hate, I think we can. Huh?
Like a bottle of water or something?
Well, I've got something to drink down in the office, so let me, if you don't mind, I hate to do it, but let me run down and get a swig of something. Well, wait. Right when I say that. Here's the fence, right? Okay. Sorry about this, Vince. My throat is getting awfully dry, so I wanted to go get a swig of water or something, so I was just getting ready to walk out. You walk, rain and thunderstorms today. The sky was almost perfectly clear this morning, and to hear them say that, so you know.
But then to look now, though, it's
Yeah.
It's
dark out there.
Yeah. Okay. So example 3. Moving a space module into orbit is what this one is. Space module weighs 15. Oh. Oh my goodness. Quick. A space module weighs 15 metric tons on the surface of the Earth. How much work is done by propelling the module to a height of 800 miles above the Earth, as shown in the figure that they have in the book that I'm not about to draw, okay? Okay? Ooh, man. It would be help. Do y'all all have, yeah, most of you do have your text or an ebook or something like that. Okay. Okay. That's the one that shows the planet Earth, and shows it, propelled it from the middle of the Atlantic Ocean, which is a very reasonable place to do it, but it doesn't matter. Use 4,000 miles as the radius of the Earth, and do not consider the effect of air resistance or the weight of the propellant. So that's two pretty big things you are not to consider, okay? But anyway. So, all we're doing is the force is varying because the further you get from the Earth, remember, the Newton's gravitational constant forced you to gravity, I'm going to put it this way, remember, was G times M1 times M2 over R squared, right? Or they called it D squared. Okay, distance squared. Well, this, remember, is a universal gravitational constant, okay? This is the mass of the spacecraft, and this is the mass of the Earth. Now, neither one of those are changing much, okay? Now, like they said, ignore the propellant, because you are losing propellant as you go. And I don't know, and that is quite a bit, and I don't know if in to a height of 800 miles above the Earth, I would have thought you would have ejected at least one stage by then. I may be wrong, but I think you would have. And that would be a huge amount of weight, okay? But guess what? All that's negligible compared to the mass of the Earth. So that's why it's not a bad idea to ignore that little bit of propellant and a little bit of a thing, because really the Earth's mass is going to overwhelm all of it whatsoever. And so that doesn't really matter that much. And then, so we're going to count these three things as a constant, okay? Even though this is varying a little bit, this is not, and that is not, okay? So, what that leads to, and this is where they get what they do in the book, some constant over, now they're calling it an x squared, okay, rather than d squared or r squared, it's calling it x squared. Okay. Now, so that's your variable force as a function of x. Okay. Now, if you'll note here, let's see. How much work is done propelling the module to a height of 800 miles above the Earth and use 4,000 miles as the radius of the Earth? Here I will sort of draw this. Oh, I see what that is. That's the center of the Earth. That's not the launch pad. I see. Now, if that's the Earth, center of the Earth is 4,000 miles, and you're going another 800 miles up here above the surface of the Earth. So, I'm sorry. So the work done is the integral from, see, you're only launching from the Earth to that 800 miles up. So it's from 4,000 to 4,800. That's the amount, that's the 800 miles you're going above the surface of the Earth, from there to there. And this is where your cx squared, that is the force you're exerting times the incremental distance you're going between 4,000 and 4,800. So that's where you get your the integral from. But what I'm trying to see here okay. They're coming up with a value for that constant C. Okay. It's sort of like we did with the spring constant problem, only a lot weirder. Okay. So rather than using G and the mass of the Earth, they're going to do the spring not the spring constant, the gravitational constant C this way, which is okay. It's fine. So since this is 15 metric tons on the surface of the Earth, the little bit of physicist that's in me, this is driving me nuts, because if you look at these units, metric tons is a SI unit. Okay, that's not your standard 2,000-pound ton. You know, that it's a metric ton. Okay, which is close to that, but not quite the same. It's about 2,200 pounds. But they're using that, and they're using miles, which is a SI, which is a U.S. customary unit, and they're just doing these willy-nilly here. It really doesn't matter. You're just coming up with a number. So the 15 is equal to C when you're at the surface of the Earth, which is 4,000 miles from its center, squared. Okay, so then this would be C is equal to 15, I can't write, 15 times 1,600,000. 16 million, okay? And multiply those out, and 16 times 15, I should know that, but I don't remember what it is. Is that 24? $240? Yeah, I guess so. 15 times 15 is 2,500. 16 times 16 is 6,400. Okay. Someone do that. 15 times 16, what you get?
240.
Huh?
240.
240? Okay. So that would be 240 million. Okay. That is your C. That's what C is. Okay. And that's what they have here too. Just didn't remember that as being the number. All right. So then the work is you can pull that 240 million out of the integral. Thank you very much. I don't want to carry it around. And then you integrate from the 4,000 to the 4,800. surface of the Earth to 800 miles above the surface of the Earth, and it's dx over x squared. And what in the world is that? Well, I don't like writing it that way. How would you write it? Make it easier to do the antiderivative? X to the minus 2 dx. Okay? And what does that antiderivative of that?
X to the minus 1.
X to the minus what?
1.
Minus 1, good. And minus x to the minus 1, right? Okay. And that's from 4,800, 4,040 to 4,800. Okay. Now, don't worry about the minus sign yet, because when you plug in, you'll see that's 1 over 4,800. So minus that, plus 1 over 4,000. And when you do that, you'll see it actually works out better that way. And all that is multiplied by your 240 million. Okay, yips. Okay. Now, I'm debating whether it's better to factor out on 100 out of that and then have 1 over 48 minus 1 over 48 plus 1 over 40. I think that's a legal move, so you can wipe out 2 of these zeros here and move your decimal point to that. And someone do that quickly, or however you want to do it. But 1 over 40 minus 1 over 48.
Over 48 minus 1 over 40 or backwards?
Say again?
1 over 48 minus 1 over 40? Or
No, you see the plus is with the 40, 1 over 40. So 1 over 40 minus 1 over 48. You'll see it turns out being a positive number, right? I hope.
Yeah, I guess it
Yeah.
is.
Right. Pretty small number, I think.
0.004.
Say that again.
0.00416.
Okay. Take that and multiply it by 2.4 million. 2, 4, and then 5 zeros.
Equals 10,000.
What's that?
10,000.
10,000
Yes.
and 50? Is that what you said? Just 10,000?
10,000.
10,000 on the nose.
With like a 8 at the very end, like, is it like 4 zeros behind the decimal and then an 8?
Okay. So that's what they got too. And look at the units. Miles, tons, which is an incredibly dumb unit, especially when you consider those are metric tons. So mile metric tons, that's okay, I guess. And then they convert to foot pounds. Feet, I understand the metric ton is 2205 pounds, which is about right. I was going to estimate 2,200 pounds. 2205 is more precise. So that gives you something like 1.164 times 10 to the 11th foot-pounds. And then if you convert that to joules, which, yay, what a fun thing to do, is 1.587 times 10 to the 11th joules. Now, why they choose to go to these incredibly bizarre numbers, I don't know, but it's fine. And I never would have thought of dealing with mile metric tons. I would have handled it differently at the beginning, but I was trying to do it the way the book did. But it does come out being that. And it's even more amazing, it comes out to be 10,000 on the nose, you know, or at least to some weird decimal point. Okay. The rest of it is, I mean, just doing conversions. Do y'all need to see how you do the conversions? I mean, is that something that y'all are struggle with, or are you okay with it? Or you want to see it at least once?
At least once.
Huh? At least once. Okay, you're all right with mile metric tons. Okay. I'm going to need a lot more room, so I'm going to, that's easy for me to remember, so I'm going to erase everything. Okay, we'll do 10,000 mile, and I have to say metric ton. If you say mile ton, that means tons, but these are metric tons, which are not the same. Okay, now we're going to multiply that by 2 conversion factors, trying to get an answer in foot pounds. Okay? Now they gave you the conversions right there. The first is going to convert miles to feet. So we'll use these first 2. Now I put 2 blanks here. The first blank is for numbers, the second blank is for units. Right? You see, we start with mile metric tons, and you're trying to get the foot pounds. So we're always put the units in their place. The first of those conversions, and this is something that most of you probably don't know, but back when I was growing up, you almost had to know it. What you want to do is put the miles in the denominator, so they're going to cancel out, and put your feet in the numerator, because that's where you want it down here. So always put the units in the place where you want them. Then match the numbers with the unit. 5,280 feet is 1 mile. Okay, so that's your first conversion. The next conversion, you're trying to get from metric tons to pounds. So where would you put the metric tons?
Tons in the bottom.
At the bottom.
And
And pounds
pounds at the top.
at the top. Okay, they give you the conversion in the book. 1 metric ton is 2,205 pounds. Never have I seen that expressed that way. Sorry, that'll come back on every time I move the thing. It makes it flash on and off. So now what you do is multiply by numerators and divide by denominators. So it's a pretty easy thing to multiply 2250 on a calculator by 5,280. So do that. 5,280 times 2205. It'll be a pretty big number.
It's 11,642,400.
Okay. So you said 11 million and what?
642,000.
Okay, leave it there. So that's going to be times 10 to the 6. I just left it in millions. And multiply that times 10 to the 5th. No, 1, 2, 3, 4, 4th. And that would give you, okay, we'll go on and move this one more place and make it to the 7th. That gives you 1.1646 times 10 to the 11th foot-pounds. Okay. And what did they get in the book? 1.164. Well, that last 6, they didn't bring it down. Okay. Now, so we'll use their numbers, 1.164 times 10 to the 11th foot-pounds. And we're going to make one more conversion to get it to joules, which are Newton meters, but they're just going to use joules. So what unit goes where? Always put the units in their place.
So the joule goes on top.
Joules on top and foot-pounds on the bottom. And they tell us here that 1 foot-pound is 1.35582 joules. So there's your conversion. Multiply those together, and hopefully you do get the same answer they do. Something on the order of 1.578.
Um,
1.35582 times 1.164.
Not times 10 to the 11.
Second.
Not times 10 to the 11.
We can just add that at the end. You're just multiplying these two, and then we'll put times 10 to 11. You could put it if you wanted to. It doesn't hurt. But that's just extra button pushing, and I can just write it in.
1.578.
7, 8. Is that what they got? Yeah, look at that. 7, 8. And then just bring down times 10 to the 11. If that had been something greater than 10, then you would have to change your exponent by 1 or something. So that's 1.578 times 10 to the 11th joules. An awful lot of joules. An awful lot of foot-pounds, okay? So.
Well, it's black outside.
Yeah, and can you hear the breeze? I thought that was here or the painter limit. I can hear the breeze from outside.
What's that?
I can hear the breeze from outside.
Oh, you can?
Yeah, you see the tree shaking it, but
Yeah. My hearing is such that I can't hear it. Usually I can hear the windows when they start doing that, but someone put a piece of paper in that and to keep it, 2 pieces, to keep it from jiggling as much. Yeah. Okay. Oh, and did that do it for us? Okay, let's just hit these last 2 slides here. And that's this. The summation of the increments to form the delta W is this increment of work is force times the distance increment, F times dx. Another way to formulate the increment of work is to do the increment of work is the force increment times the distance, delta F times your total distance F. Now that's if you're, it's a little bizarre, but good. The second interpretation of delta W is useful in problems involving movement of non-rigid substances such as fluids and chains over given distances. So then you would do delta F times X rather than F times delta X. I don't know if they're going to give an example like that or not. Yeah, the next one will be that. So maybe we should just stop there and use that as an intro to example 4. All right. So, sorry I had to take a break there in the middle.